Okay, problem 3. What's the intermediate value theorem? It's just, let's say you have 2 points A and B. Let's say you know FA is smaller than 0. Right? You know FB is strictly greater than 0. So this is your FB. So at point B, FB is here. Right? At point A, FA, so this is your FA. Right? It is here. So you know F, and you also know, so FA, let's say it's smaller than 0, FB is greater than 0. Right? And you also know that Fx is continuous. Right? Fx is continuous. Then you connect A and B, right? No matter how you connect, you will see it always intersects with x-axis at some point between A, B, right? You connect it like this. As long as this function is continuous, it intersects here. Right? You're connecting this way, it intersects here. So no matter how you connect A and B, right, these 2 points, you will always intersect. You will always meet the x-axis somewhere between A and B, right? So if, right, then there exists. Then there exists. So this means there exists. Right. So this means there exists a point C. Okay, so a point C between A, B. We don't know this point, but we know there exists such a point strictly between A, B, such that, okay, this is such that FC is 0, right? So it just means no matter how you connect these 2 functions, you will find a C such that FC is 0, right? So you do it this way, then this is your C, FC is 0. So you don't know where is this point C, but you know this point exists. Okay, so let's try it. So show that there exists a root of 1 minus x cubed equals sine x in the interval 0, 1. Okay, so in the end, our conclusion is fx equals 0 has a solution, right? So now this is not fx equal to 0. So first we change it to fx equal to 0. So it's 1 minus x cubed minus sine x equals 0, right? The root of this, it's same as the root of this. The root of this equation is same as the root of this equation, right? Okay, then, so this part is your fx. Okay, right, by the way, coming back to the graph, if fa is smaller than 0, fp is greater than 0. But if we change it, right, if this is your fa, right, if this is your fa, this is your fb, the theory is also valid, right? This theory is also valid. So it doesn't matter fa is on top, fb is at bottom, or the other way. So actually this, right, if fa is smaller than 0, fp is greater than 0, or fa is greater than 0, fp is smaller than 0. Right. So we don't want to write this, right, in this complicated sentence. So to summarize this, it's just fa times fb is smaller than 0. Okay. So it's if fa times fb is smaller than 0 and fx is continuous, then you have this point C. Okay, blah blah blah. So first we have to figure out what is f0. F0 is 1 minus 0 cubed minus sine 0. Okay, so it's 1. F1 it's 1 minus 1 cube minus sine 1, so it's negative sine 1. Without calculation, I know it is smaller than 0, right? So f0 times f1, it's smaller than 0, and right, and this fx, because it's a combination of basic functions, it's continuous. It is continuous on the interval from 0 to 1. Okay. So, right, so there exists some c between a0, 1 such that fc is 0. Right, what is fc is 0? It's 1 minus c cubed minus sine c is 0, which is 1 minus c cubed equals sine c. Okay, so c, and this c is between 0 and 1, right? So you have proof this function has a root between 0 and 1. Okay. Okay, problem 4. So x cubed minus 15x, right, plus 1 equals 0. So you have to prove it has at least 3 solutions. Right? You have to prove it has at least 3 solutions. In the interval from negative 4 to 4. So back in problem 3, so when we check this graph, this theorem tells us at least 1 solution, right? But it doesn't tell us there are 2 solutions or there are 3 solutions. It doesn't tell us the exact number of solutions. It only tells us there is at least 1 solution. Okay. So here, if we want to prove at least 3 solutions, we have to apply this theorem on different intervals 3 times. Okay, because each time the solution just guarantee at least 1 solution at each subinterval. So what is a subinterval? We can just calculate the value. Right? What is f negative 4? It's negative 4 to the power of 3, right? Minus 15 negative 4 plus 1. So this is plus 60. This is 64. Sorry, yeah, it's minus 64, right? Plus 1, so it's minus 3. So f negative 3 okay, so it is 19, right? Okay, so you can see f4 is smaller than 0, right? F negative 3 is greater than 0. So by, right, this function is obviously it's a continuous function. Right? By the way, this is your fx. Right, this function polynomial is an obvious continuous function. So by the intermediate value theorem, right, there exists a solution C between negative 3, negative 4, and negative 3 such that fc, right, is 0. So you can keep on your calculation. Keep on doing your calculation. It is right, so it's positive. Right, it's 15, it's positive. F0 is 1, right? It's positive. What about F1? F1 it's 1 cubed minus 15, 1 plus 1. Right, it is negative 13, which is smaller than 0. So you can see by IVT, right, by intermediate value theorem, because these two they have the opposite sign, right? So there exists a C between 0 and 1 such that FC is 0. Okay, keep on. F2 is 2 square minus 15 times 2. Right, so you can see F2 is not impossible. Sorry, F2 it's almost impossible. So let's try F4, right? Just F4. F4 is so it is 5. It's greater than 0. So here, by IVT, by intermediate value theorem, there exists a C between 0, 1, and 4 such that FC is 0. Okay. Alright. So you can see there exists at least 3 solutions.